everyone, welcome back to the channel. Today we're going to cover everything you need to know for physics paper 1 Combined Science. This video covers the content for both higher and foundation tiers. Paper 1 includes 4 major topics: energy, electricity, particle model of matter, and atomic structure. In this video, I'll break each one down simply and clearly, highlight the key formula you need to know, and we'll finish with a mini quiz to test your skills. Let's dive into our first topic, energy. This one's a big deal because energy questions pop up everywhere in paper 1, and honestly, once you get your basics, they're not too bad. So let's break it down super clearly. There are 8 stores of energy: kinetic energy, which is the energy of any moving object; chemical energy, energy stored in a battery or energy in food; electrostatic energy, due to attractive and repulsive forces between charges; magnetic energy, elastic potential energy, when an object is stretched or squashed; gravitational potential energy, when an object is at a height in a gravitational field; and nuclear energy. Finally, thermal energy. The next thing you need to know is how energy can be transferred from one store to another. It can be done mechanically by forces doing work electrically when there's a potential difference and charges are moving. Heating and radiation. This is the law of conservation of energy. Let's look at an example. Now, imagine you have a candle. The candle uses chemical energy in wax and it's converted into heat and light. Now, if the amount of chemical energy is 100 joules and the heat energy is 60 joules, what is the amount of light energy? So the idea is energy cannot be created or destroyed. This one is 60. Obviously, this is going to be 40 joules. Now, here is an example to apply the law of conservation of energy. Think about a pendulum. Look at the example here, and it says at the lowest position here, the gravitational potential energy is 0 because the height is 0. That is the bottom level. And the kinetic energy is 10 joules as it is moving fastest here. Now, what's the kinetic energy at the very top? Because the pendulum will move like that and it will stop here before it turns back. Remember, kinetic energy is all about movement, and if there's no movement, no kinetic energy. So that one is 0 joules. However, the total amount of energy is 10.0, add 10 is 10. So everything here is gravitational potential energy. Same thing here, GPE is 10 joules, kinetic energy is 0 joules. Now, in a position like this, somewhere in the middle, if they say that GPE is 3 joules, what is the kinetic energy? Remember, the total must be 10. So the kinetic energy has to be 7 joules. So the point is the total energy is always 10 in this example. 10 and 0 is 10, 3 add 7 is 10, 0 add 10 is 10, 10 add 0 is 10. So at any point in this particular example, the total energy is the same. So energy is conserved. Alright, the examiners love these energy equations, so let's go through them nice and easy. Here is the first one. Gravitational potential energy is found using the formula mgh. M is the mass in kilograms. G is the gravitational field strength, which is 10 newtons per kilogram on the Earth approximately. And this h here is the height in meters. Now, I remember some years ago, and I think probably 2015 or 16, one of the questions for 1 mark was, what does this lowercase g stand for? And you know what many students said? They said gravity. And unfortunately, that did not get them the mark. So please remember, this g here is gravitational field strength, which is always 10 newtons per kilogram on the Earth. Now here's an example. A person of mass 60 kilograms is on a ledge that is 120 centimeters above the ground level. What is the GPE of the person? So M is 60, G on the Earth is always 10, the value of H is 1.2. Now you need to be very careful here. Why did I put 1.2? Because it has to be in meters, so you need to divide centimeters by 100, so it's 1.2. So the answer here is 720 joules. Next one is kinetic energy. Kinetic energy is defined as the energy obtained by mass due to its movement. So if a mass of m is travelling at speed v, the kinetic energy is given by the formula half mv squared. Again, units are very important. Energy is always measured in joules. Half is a number. Mass is measured in kilograms. If they gave it in grams, you have to divide it by 1000 to do the conversion. And this V here is speed, and speed is measured in meters per second. So step 1, the formula KE equals half mv squared. Now we need to substitute the values half times 1000 times 20 squared, which gives you 200,000 joules. Next one is elastic potential energy. This is defined as energy obtained by an object due to its shape. That is when it is stretched or squashed. Imagine you have a spring of spring constant K. Now the spring constant is a value which gives you an idea about how hard or easy to stretch it or squash it. Something with a high spring constant is hard to stretch. Now if you exert a force on it, it will extend. Now this extra length that it gains when you exert a force on it is called the extension. We normally use the letter X here. Sometimes we use E. They are both okay. Now, to find the elastic potential energy of a spring, we can use the formula EPE is equal to half Fx. F is the force exerted. Now there is another variation of this formula. That is EPE is equal to half kx squared. So you can see in the second one we use k and x. So one might ask, why do we need two formulae? If you know f and x, you need to use the first one. If you know k and x, you can use the second one. Now let's look at an example. You have a spring of spring constant k, 200 newtons per meter, and you exert a force and it extends by 10 centimeters. Find the amount of elastic potential energy. So we have EPE is equal to half Fx, or EPE equals half kx squared. Now we can clearly see, I know k, I know x, so obviously it has to be the one with k and x, and not this one. We are going to use this one, so let's do that. EPE is equal to half times, k is 200 times x squared. Now this is really important, x is 10 centimeters, but it should be in meters. Divide by 100, 0.1 squared, and the answer is 1 joule. Now here's a quick summary of what we discussed. GPE is given by the formula mgh. Kinetic energy is given by the formula half mv squared. Elastic potential energy is given by one of these two formulae. EPE equals half Fx, or EPE equals half kx squared. The next thing you need to know is work done. Now in physics, work is done when you exert a force and move something through a distance. And we can use the formula work done is equal to force multiplied by distance moved in the direction of the force. Obviously work is the same as energy transferred measured in joules. Force is measured in newtons. The distance is measured in meters. Imagine you exert a force of 20 newtons and move an object through a distance of 60 centimeters. So what is the work done? The answer is 12 joules. The next subtopic is power. In physics, power is defined as the rate of doing work, or rate of energy transfer. So whenever we use the word rate, that means you divide by time. So we need to know these two formulae. Power is equal to work done divided by time, or power is equal to energy divided by time. Efficiency is defined as the proportion of the input energy that is converted into useful forms. Think about a car, maybe a petrol car. So the amount of chemical energy input is 1000 joules. It gives out kinetic energy, thermal energy, and sound energy. Now obviously thermal energy and sound energy are not useful. The only useful form here is kinetic energy. So to calculate efficiency, you need to use the following formula. Efficiency is useful output divided by the total input. Now what's the useful output? 600? Yeah. What's the total input? It's 1000. So the answer is 0.6. And you don't have any units because the units, joules, get cancelled out. Now in some instances they can ask you to calculate the percentage efficiency. Now this is really easy. To convert a fraction to a percentage, you always multiply by 100. It's the same formula, you just have 100 at the end. So the answer is 600 divided by 1000 multiplied by 100, and the answer is 60%. So the percentage efficiency is 60%. Efficiency itself is 0.6. Here is a really important thing you need to memorise. Efficiency can never be more than 1. The definition of specific heat capacity is the amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. The specific heat capacity of water is 4,200 joules per kilogram degree Celsius. Here's the formula for specific heat capacity. E is the amount of energy measured in joules. M is the mass in kilograms. C is the specific heat capacity in joules per kilogram. Delta theta is the change in temperature in degrees Celsius. This whole thing is together and it stands for the change in temperature. Find the amount of energy needed to heat 200 grams of water from 23 to 83 degrees Celsius. So step 1, write the formula. Now let's substitute values. M is the mass. I should put 0.2. Why 0.2? Because it's in kilograms and here it's given in grams. So 200 divided by 1000 is 0.2 times specific heat capacity C of water, 4,200 multiplied by delta theta. Delta theta is the change in temperature, so it goes from 23 to 83. So let's find the difference. All I need to do is 83 take away 23 and it's 50,400 joules. The aim of this experiment is to determine the specific heat capacity of aluminium. Insert the immersion heater into the larger hole at the top of the metal block. So here's the heater which heats up. To measure the temperature, we need a thermometer. So you insert a thermometer and you add few drops of oil to ensure good thermal contact. Now the idea is, if you look at it closely, the bulb of the thermometer will be like this. Now the hole is a bit larger than that, so there is no good thermal contact as it's usually filled with air. Now air is a poor conductor, so what we do is add a couple of drops of oil to make sure that this space gets filled up. Now we need to use cotton wool to lag it. Measure and record the starting temperature of the block. So that's the first thermometer reading. Then you turn the power supply on and then let it go for a certain period of time, say 10 minutes. Now during this time you need to get the readings from the ammeter and the voltmeter. There will be an ammeter and voltmeter connected. Then you turn the heater off and you wait for the thermometer to reach the highest rating. Remember, even after the heat is turned off, the temperature can still rise. So you need to watch for the maximum temperature. So the thermometer will go up to a maximum value and start to drop, and you record that maximum value. Let's say the mass of the metal block is 2 kilograms. Initial temperature was 20. Final temperature maximum was 32. Current and voltmeter readings are given and the heat was on for 600 seconds. Now remember, my intention is to find specific heat capacity C. E is equal to mc delta theta, and this energy is supplied by the electrical supply. So for electrical energy, E is equal to VIT. Now let's substitute the values. Here the energy supplied is 12 volts multiplied by 2 amps multiplied by 600 seconds. Now I can substitute this 14,400 for energy. Here 14,400 is equal to M times C times delta theta. For change in temperature, 32 take away 20 is 12. You can do the calculation and the value of C can be calculated. The next thing you need to know is about reducing unwanted energy transfers from buildings. Now for this, you need to know the methods that we use to reduce it. For an example, the energy lost through the walls can be reduced by using cavity wall insulation. So basically you have the 2 layers of brick and we have some foam in the middle. Here's one layer, here's the other layer, and the gap in the middle is filled with a type of foam to reduce energy loss. Hot water tank jackets are used to insulate hot water tanks to reduce energy loss. The pipes that are used for carrying hot water, the copper pipes, are covered by foam. We call it pipe lagging. Double glazing, you have 2 panes of glass and then low pressure air in the middle to reduce the energy loss. Draft excluders, you can see them in the post boxes or sometimes under the doors of buses. And then for the roof, we use loft insulation. Energy resources can be divided into 2 main groups as renewable and non-renewable resources. As the name implies, renewable resources are the ones that do not run out. Non-renewable energy resources are the ones that cannot be replaced quick enough, and they will eventually run out. For an example, coal, oil, gas and nuclear energy resources, wind energy, wind turbines, solar energy, which can be used for electricity production and also solar heating. Biofuel. So these are the biological substances, like the things that you get from trees that can be used as a fuel. For example, used cooking oil can be converted into biodiesel things. Ethanol is an example of another biofuel. Wave energy, tidal energy. Now these two, sometimes students get them a bit mixed up. They are actually slightly different. In wave energy, we use the energy of the moving waves to produce electricity. In tidal energy, it is the high tide and low tide. So when the sea level goes up in high tide, you capture the water using tidal barrages, and when the other side goes down, you release that energy, and we can convert that gravitational potential energy of the water at the high level into kinetic energy, which is converted into electrical energy. Coal, oil and gas. Collectively, we call them fossil fuels. Now these are the non-renewable ones: coal, oil, gas and nuclear. Hydroelectricity. We use gravitational potential energy of water at a high level, and geothermal energy is the energy that we get from the heat inside the Earth's surface. So basically, radioactivity of the rocks produce heat energy. We use that heat energy to heat water, which is then turned into steam, and we can use that steam to drive a turbine. Advantages and disadvantages of different energy sources is another popular exam question. Solar power is renewable and it's sustainable. That means it will not run out. It has low maintenance once installed. Ideal for small scale setups like road signs, because you don't need to have wiring to connect to the national grid. You can have it anywhere you want, can be built into roofs or walls. You can sort of integrate it. It has a minimal visual impact, no fuel cost, no air pollution during operation, like no carbon dioxide. Now remember, in the exam, don't just say no pollution, which is not specific enough. It's kind of vague. You need to say that something does not produce greenhouse gases like CO2. Be very specific. Disadvantages: high initial cost, not reliable, depends on the sun and requires a large area due to low efficiency. Wind power. It's renewable, low maintenance cost and no fuel cost. No CO2. Cons are visual pollution and noise pollution. Also, it's not reliable, depends on the wind and limited possible locations. You can't use it from in any place you like. Usually the ideal locations for these are the most expensive land, like the ones in the seashore. They can harm birds due to spinning turbine blades. Unfortunately, sometimes we can find dead birds under wind turbines. Wave power, renewable, sustainable, no fuel cost, no carbon dioxide or any other atmospheric pollutants. Disadvantages: it's difficult to transfer energy from the sea to where you need it, probably to a far place in the land. It's unreliable, depends on the wave conditions, limited suitable locations for installation. Can disrupt marine ecosystems because it can be harmful to fish, corals and other sea life. Tidal energy, renewable, no fuel cost, no CO2. It can help to regulate the estuary water levels, and it's more reliable than other renewable energy because there is a pattern. Disadvantages: can have a large impact on ecosystems. It does not always generate power when it's most needed because you can't really change when you get the most of the energy, and there are few suitable locations for installation. You might need to actually quickly pause this video for these things because I'm kind of quickly talking this through. So to absorb it, you might need to pause the video, have a look and then press play. Hydroelectricity, renewable, no fuel cost, no atmospheric pollutant like carbon dioxide. It can create lakes for recreation, which is a positive thing. It's generally reliable. Disadvantages: can have a major impact on ecosystems because you're flooding large areas, limited locations. These are often built far from cities, so we have to transfer energy. There's a transfer issue, which means there will be loss of energy, risk of flooding when you build the dam. Fossil fuels generate a large amount of energy at low cost, so it's energy dense, reliable, it's not affected by weather, you can use it whenever you want it. Existing infrastructure. Many power stations have already been built, so you don't need to spend money to make new ones, and it's relatively safe to transport in comparison to things like nuclear power, for example. Disadvantages: it releases carbon dioxide, which is a greenhouse gas, causes global warming. Climate change: burning coal and oil produces SO2, which causes acid rain, and it's non-renewable. And finally, nuclear power do not release air pollutants like CO2. They are very efficient, very energy dense, and is reliable. Disadvantages: they produce radioactive waste, which is dangerous, costly to manage. And also they can remain in the environment for hundreds, if not thousands of years. Risk of nuclear accidents like Chernobyl, high startup and shutdown cost. So the startup cost of a nuclear power station is pretty high. And also, at the end of the life of this nuclear power station, the decommissioning is also a very costly process. Here is a mini quiz to check your understanding on the energy topic. We are done with the topic now. Please pause the video and give these a try. When you are ready for the answers, press play. Here are the correct answers. Please take a minute to check your answers, and if you have any doubts or questions regarding this, you can always ask me in the comment section and I will try and answer. Also, I will leave links in the description. Alright, next up, electricity. Now listen, I promise, electricity is not scary as it looks at first. It's mostly just a few key ideas and a handful of formulae that you'll be using over and over again. Let's break it down nice and easy. An electric current is defined as the rate of flow of charge. So remember, rate means you divide by time. The formula for electric current is I is equal to Q over T. Charge is measured in coulombs. Time is measured in seconds. Current is measured in amps. Now, let's think about a power supply. The negative terminal has a high electron pressure. There are a lot of electrons. The positive terminal is electron deficient. There are not enough electrons. Because electrons are negatively charged, the electrons here are attracted towards the positive terminal, and electrons are repelled away from the negative. So obviously the flow of electrons, as you can see by this red arrow, is from negative to positive. So here is the conclusion of that. Now, the direction of the conventional current is the other way around. Now I know this is a little confusing for most students, but the idea is that the flow of electrons is opposite to the conventional current, because historically, current was defined before electrons were discovered. So scientists assumed that current flows from positive to negative, which became known as the conventional current. Later, it was found that electrons actually move from negative to positive. If they ask specifically in the exam about the flow of electrons, it's from negative to positive like this. But otherwise, usually, the current is always from positive to negative. And here's the next basic formula. You need to know potential difference or voltage. So by definition, potential difference is the work done per unit charge. It's simply the work done divided by charge. V is equal to W over Q. The units are joules for work done, coulombs for charge, and volts for voltage. So here you can see the symbols you need to know for GCSE electricity. Pause the video and take a minute to quickly think about each one and whether you know the names of them, and when you are ready to check the answers, press play. Here are the answers. Open switch, closed switch. A cell is here, and this one here is a battery. The difference is that a battery consists of two or more cells connected together. A diode, resistor, variable resistor. It's easy to memorise this because a variable resistor has this control arrow, which means the resistance can be changed. Lamp here. This one is a fuse. It's just like a resistor, but the line goes all the way through ammeter, voltmeter and motor. These are very obvious. And this one is a thermistor. This is a popular exam question. I've seen this in past papers as a 1-mark question. They usually ask you to draw the symbol of a thermistor or a fuse. Next one is just like a resistor here, and light is incident on it. So obviously it's a light dependent resistor, or LDR. And the next one is an LED. Here you can see the diode, and here's the same diode. But what's this? This is light going out. Light is being emitted. So light emitting diode, or LED, resistance is the property of the material that opposes the flow of current through it. Mathematically, resistance is defined as voltage divided by current. R is equal to V divided by I, or you can even rearrange this to the form V is equal to I times R. You get lots of exam questions from this formula. The current through a component is directly proportional to the PD across its ends if temperature and other physical quantities remain constant. So V is directly proportional to I. That means V is equal to some constant times I. I remember in one of the years, again this was probably like 8 to 9 years ago, usually they have been asking voltage in the y-axis and current in the x-axis in the past, and that year they switched them. And you know, when it's V is equal to IR, and you can see here when it's VI graph, the gradient gives you R. However, in IV graph, the gradient gives you the reciprocal of R. Resistors are divided into two main categories as ohmic and non-ohmic. Ohmic resistors obey Ohm's law. So the current voltage graph is a straight line through the origin. For example, a metallic conductor at constant temperature. Examples of non-ohmic resistors are filament lamps and diodes. In a filament lamp, the current increases with potential difference, but then what happens is it kind of comes to a plateau around here, because as the temperature increases, the resistance increases. A diode is a slightly peculiar one compared to the others, because this graph is asymmetrical. Investigating IV graphs. To do this experiment, you need this experimental setup, a power supply, and this is a component that is being checked. In this example, it is a resistor. A voltmeter is connected in parallel and an ammeter is connected in series, and a variable resistor here to change the resistance. So what we need to do is change the value of R, and you can record the PD and current. You can replace the resistor with a filament lamp, and then you can produce a VI graph for that. Here's the next experiment using a wire mounted on a meter rule. And this one here is what we call a sliding contact. Now first you can connect the sliding contact to the 100 centimeter mark. So you can use the full length of the wire like this. Then you record the length, record the PD and current. Now resistance is equal to V over I, so I can divide the voltage by the current to work out the resistance at that point. Then you move this to 90 centimeters, and then you record the length, PD and current, and then you can calculate the resistance, and you repeat it like that all the way down to 10 centimeters. Then you can plot a graph of resistance against length. So here you will get a straight line graph through the origin with a positive gradient. The difference between series and parallel circuits is a really important thing in physics. Now in a series circuit, components are placed one after the other, and there is only one path for the current to flow, and the current through each component is the same. If the current starts from here, there's only one path here. It's 2 amps here, 2 amps through this one through this, and everywhere the current is the same. It is 2 amps. But in a parallel circuit, components are placed side by side. So this one and this one and this one are side by side. And there are multiple paths due to junctions. So the current can come like that and the current can split up. So you get 2 amps here, 3 amps here, that can again split up depending on the resistance. 1 amp here, 2 amps here, like that. So the current splits up. Now in a series circuit, voltage splits up. Now you can see there is 10 volts and it splits up as 3, 5 and 2. However, in a parallel circuit, voltage does not split up. You see there is a 6 volt power supply, and here is 6. Here is also 6. The other one also fills the full 6. If a fault develops in one component in a series circuit, all others will not work. Now imagine if this one broke for some reason. There is no path for the current to go. Now the current cannot flow because of the gap, so everything else will also stop working. However, in a parallel circuit, if a fault develops in one component, the others will still work. Now let's say this one got damaged for some reason. Now the current cannot go through that branch, but here the current can still go through the other branches like this one and the other one, so others will still work. In a series circuit, all components are controlled by one switch together. Now let's say if you put a switch here in the circuit, it will control the circuit altogether. However, in a parallel circuit, each individual component can be controlled by separate switches. Now let's say you put a switch here that will only control this. Here is the typical GCSE exam style question on series circuits. If you want, pause the video and give it a try. Step 1 is to find the total resistance. So how do you find the total resistance? There's 4 ohms here, 6 ohms here. So the total resistance is 10 ohms. Step 2 is using V is equal to I times R for the whole circuit. So let's do that. Voltage provided is 20 volts. The current, I don't know, R is now 10. So if you divide both sides by 10, I is equal to 2 amps. So I know the reading on each ammeter is 2 amps. So in the last step, to find each voltmeter readings you're going to use, V is equal to I times R for each resistor. Let's do it. For this one, V1 is I times R, so 2 times 4 is 8 volts. This one is 2 times 6, 12 volts. Now here you can see a typical GCSE exam style parallel circuit question. Again, pause the video and give it a try. When you're ready for the answer, you can press play. Now remember, in a parallel circuit, the voltage across each branch is the same. So this is 8 volts. Obviously, voltmeter 1 is 8 volts. Voltmeter 2 reading is also 8 volts. So I'm now going to find the current in each branch. So all I need to do is step 1, write V is equal to I times R. Now let's write for this one here. Now I can see the current in the branch here is 0.4 amps. Now let's do the same thing to the other one. This one V is equal to I times R. Divide both sides by 10, and you can see the current here is 0.8 amps. So the reading on A3 is 0.8 amps. Now look at this. We have 0.4 amps going down this branch, and we have 0.8 amps going through this branch. But where did those two currents come through? Those currents can only come through the branch above. So obviously the current in this branch should be the sum of these two, which is 1.2 amps. I have this easy way of explaining this, and I have found over the years that students find it's really helpful to understand it. So think about a marathon. Let's say 3 people run along this route and 4 people run along this route. Now obviously if there's only one route to come to that junction, the total number of people who ran here must be obviously 7. So just like that, 0.4 and 0.8 add up to 1.2 amps. LDRs and thermistors, light-dependent resistors. As the name implies, the intensity of light decides its resistance. In bright light, the resistance is low. In darkness, the resistance is high. Now, to understand it, let's use this example. Imagine there is a room and there is no other light source except for this one bulb. Now, it is in complete darkness to start with, and you have a light-dependent resistor on one side, and if you keep the light bulb on the other side and turn it on, so the intensity of light is low because it's far away, and the resistance could be, let's say, 10 ohms. Now, if you bring the bulb really close to the LDR so that the intensity of light is high, the resistance could now go down to 2 ohms. Thermistors, as the name implies, change the resistance depending on the temperature. Just like an LDR, when the temperature is high, it has a low resistance. In cold conditions, the resistance is high. Sensing circuits are used to respond to changes in the environment. In bright light, the LDR has a low resistance. Now let's say the resistance of the fixed resistor is 50 ohms, and let's say in bright light, the low resistance of the LDR is 2 ohms. Now look at the ratio, it's only 50 to 2. So a very small proportion of the input voltage 10 will be across the LDR. Now in this example, I did the calculation. The voltage across this LDR is about 0.4 volts. That's a very small value. Will the light bulb illuminate? No, it will not, because it's such a small PD. Now let's see what happens in darkness. When it is dark at night, the resistance of the LDR increases. Now let's say it's not 2 ohms anymore. When it's dark, it's 150 ohms. Now the size of the fixed resistor is still 50 ohms. Now you can see 3/4 of the input voltage, which is 7.5 volts, is across this one. Now that is a high voltage, so what will happen? The bulb illuminates. This is a sensing circuit using a thermistor. In hot conditions, the thermistor has a lower resistance. Now here is the thermistor. Let's say the fixed resistor has a resistance of 100 ohms. In both cases, the lower resistance is 2 ohms when it is hot. Now the input voltage is 10. Now a very small proportion, like 0.2 volts, is across the thermistor, which means most of it, 98% of it, 9.8 volts, is now across the motor. So here is the motor. So this is connected to the motor of a fan. So the fan will work when it is hot. So that's good. Now what happens when it is cold? When it is cold, the thermistor's resistance is high. Now let's say the resistance of the thermistor now becomes 300 ohms. You can see the ratio is 1 to 3. So most of this input voltage, that is 7.5 volts, is now across the 300 ohms. So what will happen? The fixed resistor has a smaller potential difference, which is only 2.5 volts. So the fan will not work. So either it will not work, or sometimes you can have an arrangement where the fan will work but at a much slower speed. DC and AC/DC stands for direct current. AC stands for alternating current. So in DC, current will start from one end and it will just flow in the circuit in one direction like that. So the current against time graph is like this. You can see the size of the current is constant over time. For example, a battery provides DC, but in an alternating current the situation is different. So the idea is this pushes the current first in one direction and the next moment in the other direction, and so on and so forth. So what happens is the current has a positive component, it goes in one direction and then it switches the direction and then the other direction again. So current first flows in one direction and then in the opposite direction. Now here you need to know that UK mains electricity is AC and the voltage is 230 volts. Frequency means the number of times that it changes direction per second. In UK mains electricity, the frequency is 50 Hz. Here's a question for you. Pause the video and think for a moment. Which of these are AC and which of these are DC? Obviously one is DC because it's in one direction. Third one is obviously AC. Now it's the second one and the fourth one that most people make mistakes on. Sometimes students think this is AC because of the shape of it. However, remember there is nothing on the negative side. Remember, it has to go to the negative side if it is AC, so this one is AC, all others are actually DC. Wiring a plug. You need to know about different wires in a plug. So this brown one is the live wire, and this blue one is the neutral wire, and the green and yellow striped one is the earth wire. Now the live wire brings the current into the appliance, neutral wire completes the circuit and takes the current out. The earth wire is basically a safety feature. The fuse here is also a safety feature. So what happens is, if the current gets too high, the fuse will melt. Then you can see here there is a cable grip to secure the cable, and the outer insulation provides extra plastic covering to make sure that the users are not touching any metal parts. Earthing and fuses. Think about a washing machine. Now let's say the working current of a washing machine is 4.5 amps. So a 4.5 amp current will go through the motor and then it will do its job. And the neutral wire brings it back out. Now here we have a fuse. So the job of a fuse is to melt if the current goes above a certain value. Here is the diagram of a fuse, and the value here is 3 amps. This is what you call the rating of the fuse. The idea is if the current goes above 3 amps, this fuse will melt. Now let's look at the design of a fuse. We have a glass cartridge, 2 metal caps, and here's a wire. This wire is designed to melt when the current goes above a certain value. Usually what we do is the rating of the fuse is kept slightly above the actual working current. Now in this example, the washing machine we have needs a working current of 4.5 amps. Let's say this is a 5 amp fuse, a bit above 4.5 amps. So under normal conditions, no problem, current will go through it and everything will work. If something happens to the washing machine and if the live wire accidentally touches the metal casing, this can be very dangerous. The next time a person touches it will get an electric shock. The prevention here is the earth wire. Here is the earth wire. So the earth wire is just connected to the metal casing. Under normal conditions, there will be no current. However, when the live wire touches the metal case accidentally, what will happen is this becomes live. A large current will surge down to the earth. Now this is literally connected to a metal pole driven into the earth. Now what will happen to this current of 4.5 amps is not 4.5 anymore. It goes up 4.7 and 4.8 and 4.9, but the moment it goes above 5 amps, the fuse melts. Now the circuit will not get any more current. Although I took a minute to explain it like that, in reality all you see is you go and turn the washing machine on, and within a fraction of a second there will be a surge of current, and then it just does not work. Now here is what you can write if they ask this in a 6-mark question in the exam. Please pause the video and take a minute to quickly read this through. Electrical power. The formula for electrical power is P is equal to I times V. Some people use an ivy leaf to memorise the formula. And then there are 2 other variations of this. So we know V is equal to I times R, and for this V, I can substitute IR. So what do I get? I times IR gives I squared R. Similarly, V is equal to IV, and V is equal to IR. So I is V over R, and I can put V over R here. So here you can see all 3 variations of this formula. Here's a typical exam style question on this. Please pause the video and give it a try. When you are ready for the answer, you can press play. Here's the answer. Now the question is to calculate the power of the resistor. Now look, we have the voltage and resistance. So what is the formula with V and R? Obviously it's this one here. So what we do, we use P is equal to V squared over R, and it's 20 squared over 8, and you get 50 watts. Power equals energy divided by time. So the power is 50 watts. I'm going to calculate the energy. Now remember, the time should be in seconds. So I know 1 hour is 60 minutes, 1 minute is 60 seconds. So 60 times 60 gives 3,600 seconds. Now 2 hours is 2 times 3,600 seconds, which is 7,200. And all you do is multiply those 2 together and you get 360,000 joules. That's the answer. The national grid. The national grid is the network that connects the power stations to homes, factories and other buildings using a system of cables and transformers all over the UK. Now they have step-up transformers and step-down transformers. So next to the power station we have a step-up transformer which increases the voltage to like a really high value. Then near the consumers there's a step-down transformer here, and that will reduce it to 230 volts. Now why do we use these high voltages for the electricity transmission? The reason is explained by the formula. P is equal to I squared R. Now you can see when you have a high current there is a lot of power dissipation. So if you use a high current, these wires will heat up and a lot of heat energy will dissipate. If you increase the voltage, what will happen to the current? Because the power is constant, the current will go down. So we use large voltages and lower currents for the transmission to reduce the energy loss. That's electricity done. Remember, lots of marks just come from remembering which formula to use and plugging them in the correct way. So keep those formulas super fresh in your brain. Here is a mini quiz on electricity. Pause the video and give it a try. Here are the answers. Alright, now we are on to the particle model of matter. This one is all about how materials behave depending on how their particles are arranged and how energy changes things like temperature and state. Sounds fancy, but honestly it is very doable once you break it down. First off, density. Density is defined as mass per unit volume. The formula for density is mass over volume. You can write it as D equals M over V. Now for the units, mass can be measured in kilograms, volume should be measured in cubic meters in that case, and your density is given in kilograms per cubic meter. Alternatively, you can use grams for mass and cubic centimeters for volume, and the density is given in grams per cubic centimeter. And here is an important unit conversion. 1 cubic meter is the same as 10 to the power of 6 cubic centimeters. So to convert cubic meters to cubic centimeters, you need to multiply by 10 to the power of 6. To convert cubic centimeters to cubic meters, you need to divide by 10 to the power of 6. Here is a question for you. Here is the answer. For the first part, it is very straightforward. 200 grams divided by 40 gives 5 grams per cubic centimeter. For the second part, you need to convert the mass into kilograms. So 200 divided by 1000 is 0.2 kilograms. Volume is 40 divided by 10 to the power of 6. The calculator gives 40 times 10 to the power of negative 6. Substitute in the formula, and you get 5,000 kilograms per cubic meter. It is important to note that usually solids have higher densities than liquids and gases, and usually gases have the least density. You can clearly see this in the diagram. To find the density of an object, we need to know the mass and volume. Finding the mass of an object is really easy. All you need to use is a top-pan balance. To find the volume of a regular shape, we can just use the length, width and height. For example, for a metal cube, you just multiply them together to get the volume. Now to find the volume of a sphere, the formula is 4/3 pi r cubed. So all we need is the radius, so you can use a vernier caliper to measure the diameter. Once you know the diameter, half it to get the radius. Now you can plug it in the formula 4/3 pi r cubed to get the volume. Then you need to substitute in the formula density of a liquid. Again, we need mass and volume because density equals mass over volume. So first you need to place an empty measuring cylinder on the top pan balance and reset the balance to be 0. Usually there is a tare button here. You can press it and it goes to 0. Now add 10 milliliters of the liquid, say up to this level. Now you have a volume reading and you have a mass. Divide mass by volume so you get the density. Then you add another 10 milliliters. That is 20 milliliters altogether. Now you have a new mass reading and can calculate the density. Then you need to use these density readings to calculate a mean density of an irregular object. Imagine you have an object that is shaped like this. Finding the mass is easy. All you need to use is a top-pan balance and record the mass. Density equals mass over volume. To find the volume, you need to use what we call a eureka can or a displacement can. So first you need to get an empty eureka can. When you fill water, it will only go up to this level, only because any excess water will obviously flow out. Then you need to take this irregularly shaped object and tie it to a string, and you need to slowly lower it into the eureka can, and make sure to put an empty measuring cylinder here to catch any water that comes out. So the volume of water that gets collected out here is exactly equal to the volume of this object. Now, use the formula to calculate the density. There is another way to do this using just a measuring cylinder. So in this case, you need to fill water up to a known level, say V1. Let's assume this is 20 cubic centimeters. Then like before, you need to tie this irregularly shaped object to a string and slowly lower it into the measuring cylinder until it is completely submerged. The water level will go up. Now, the new volume is V2. Let's say this is 30 cubic centimeters. So obviously, the volume of the object must be the difference between V2 and V1, which is 10 cubic centimeters. Now pause the video and take a minute to have a look at the properties of the 3 states of matter. You need to know about the arrangement of particles. In solids, there is a regular pattern. In liquids, it's random. And in gases, again, random movement of particles. Solids vibrate about fixed positions, but liquid particles are free to move around each other. And in gases, particles move very quickly in all directions. In solids, particles are relatively close. Liquids are moderately spaced out, and gas particles are significantly far apart. Solids have a fixed shape. Liquids take the shape of the container. Gases have no surfaces, so there is no shape. Density of solids is high. In liquids, it's moderate and low in gases. Volume of a solid is fixed. Volume of a liquid is also fixed. In a gas, there are a lot of spaces in the middle, so it can be compressed, so it is not fixed. A solid melts to turn into a liquid, and a liquid freezes to turn into a solid. A liquid can be subjected to evaporation or vaporization to turn it into a gas. A gas can be condensed to turn into a liquid. A solid can turn into a gas directly without going through the liquid phase, and we call this sublimation. The opposite of sublimation is either desublimation or deposition, specific latent heat. Think about this experimental arrangement. You have a container in which you have ice at minus 10 degrees Celsius. You put a heater here, and then there is a temperature probe connected to a data logger and a computer to measure the temperature, and then we start to heat this. Imagine it starts from minus 10 degrees Celsius, and then the temperature increases. And when it goes to 0, something peculiar happens. Although you keep on heating, the temperature does not increase. It will remain at the same level for a little while. What is really happening here is the energy that you provide is being used to break bonds and turn the solid into a liquid. So at the beginning here, everything is solid. At the end here, everything is liquid. Now once everything is liquid, the temperature will rise again. So the liquid will heat up, and the same thing happens when it hits 100 degrees Celsius. Now the liquid is being converted into gas. Vaporization is taking place. So again, the phase change takes place, and it requires energy. So the temperature does not rise. So what happens in places like this is called a phase change. Specific latent heat is divided into two categories: specific latent heat of fusion, where a solid is turning into liquid, and specific latent heat of vaporization, where a liquid is turning into a gas. Let's take an example to understand this in depth. You have 1 kilogram of ice at 0 degrees Celsius, and you need to convert it into 1 kilogram of water at the same temperature. So you can see the temperature has not changed. Remember, the graph was flat. This process requires 334,000 joules. So the definition of specific latent heat of fusion is the amount of energy needed to convert 1 kilogram of a solid at its melting point to liquid without changing its temperature. So we can say the specific latent heat of fusion of ice is 334,000 joules per kilogram. Think about 1 kilogram of water at 100 degrees Celsius at the boiling point of water. Now if you want to convert this to steam at the same temperature, the amount of energy needed is 2,260,000 joules. So the definition of specific latent heat of vaporization is the amount of energy needed to convert 1 kilogram of a liquid at its boiling point to gas without changing its temperature. So we can say the specific latent heat of vaporization of water is 2,260,000 joules per kilogram. The formula for specific latent heat is E equals m times L. E is the energy in joules, m is the mass in kilograms, and L is the specific latent heat in joules per kilogram. And you can use the same formula for both fusion and vaporization. Here is a question for you to try. Please pause the video and give it a try. Part A is very straightforward. This is a direct substitution. E equals m times L. Mass is 0.5 kilograms. It's really important that you convert grams to kilograms, and L is given. The answer is 167,000 joules. The second part, explain why the temperature of the ice does not change during melting, even though energy is being transferred. For 1 mark, you need to mention that the temperature remains constant during the change of state. The second mark, you need to explain that energy is used to break intermolecular bonds and not to increase temperature. So in a solid, the particles are like this, very close to each other. So energy is needed to overcome the forces and turn it into a liquid. Here is your mini quiz on the particle model of matter. Please pause the video. When you are ready for the answers, press play. Here are the answers. Can I please have 15 seconds of your time before the last topic? If this video has helped you so far, please give it a like and subscribe. It's totally free, takes 5 seconds, and it lets me know you want more videos to help with your GCSEs, and the channel will grow with your support. Alright, the last major topic for paper 1 is atomic structure. This one is all about the atom, what is inside it, how we discovered it, and what happens when atoms break apart. Honestly, it is a super interesting topic, and it is a great place to pick up some marks. Let's go back in time for a second. Scientists did not always know what an atom looked like. Here is a quick story. The oldest record we have is about a philosopher called Democritus, who lived from 460 to 370 BC. His idea was that atoms are small, indestructible, indivisible particles. Next, it's John Dalton. We kind of fast forward to the 1800s. Atoms are tiny, hard spheres. They cannot be split. And he also mentioned that there are different elements. J. Thomson discovered the electron, and he came up with a model called the plum pudding model. His idea was that an atom is a positively charged sphere, and electrons are embedded in it, as if plums are scattered in a pudding. Rutherford did this gold foil experiment, or we call the alpha particle scattering experiment, and he came up with the idea that most of the atom's mass is in a tiny nucleus, and most of the atom's space is empty. After a few years, Niels Bohr added the idea that energy levels exist. Then, in 1932, James Chadwick discovered the neutron. Every atom has two important numbers. The atomic number is the number of protons in an atom. For example, in carbon, the number of protons is 6. Mass number is the number at the top, which is the total number of protons and neutrons here. In this case, it is 12. So here it is, just the number of protons, and this is the sum of protons and neutrons. So obviously, if I need to find just neutrons, take away 6 from 12, and the answer is 6. Now, it is not always the same as in this example. Remember, in any atom, the number of protons and electrons are the same. So that will be 6. The number of neutrons is 12. Take away 6 gives you 6. Now, in this case, they are all the same number. Let's look at a different example. In sodium, the atomic number is 11. Mass number is 23. So the number of protons is 11. Number of electrons is the same as protons. The number of neutrons is mass number 23, take away the atomic number, and the answer is 12. Some atoms are unstable, so they randomly throw out radiation to become more stable, and this is what we call radioactive decay. So here you can see an unstable nucleus that can give out gamma radiation, beta particles, and alpha particles to become more stable. Alpha, beta, and gamma radiation. Now, you need to know about the nature of these things. Alpha particles consist of 2 protons and 2 neutrons. So this is identical to a helium nucleus. Why? If you think about a helium atom, you have 2 protons, 2 neutrons, and 2 electrons. Now, if you get rid of these 2 electrons, you are left with a nucleus, which is identical to an alpha particle. So, 2 protons and 2 neutrons. Beta particles are high speed, high energy electrons ejected from the nucleus. In the past, students have asked me how it is possible, as there are no electrons in the nucleus. Well, what really happens is a neutron in the nucleus splits into a proton and an electron, and that electron comes out as a beta particle. Gamma radiation, this is high frequency electromagnetic radiation, so there is no mass or no charge. Here you can see properties of alpha, beta, and gamma radiation. As there is a lot of information, you might need to pause the video and have a look at it after the explanation. Nature of alpha particles. 2 protons and 2 neutrons. Beta high energy electron gamma, an electromagnetic wave. The charge of an alpha particle is +2. Because there are 2 protons, beta is -1, and gamma has no charge. Relative mass alpha particles, 2 protons, 2 neutrons, so that is 4. Beta is really small and almost 0. Gamma is a wave, so no mass. The penetration power alpha radiation is stopped by a paper, or a few centimetres of air. Usually it can go about 5 centimetres in air. You can see it on the diagram on the right hand side. Alpha particles cannot penetrate the paper. Beta radiation can go through a paper with no problem, but it is usually stopped by about 3 millimeters thick aluminium. You can see here that it gets stopped by aluminium. Gamma radiation is reduced by thick lead or concrete. Ionizing power, alpha is highly ionizing, beta is moderately ionizing, gamma is the least ionizing. Range, beta radiation can go from 30 centimeters up to 1 meter. Gamma radiation can go lots of meters. If there is an electric field, alpha particles will change direction because it has a charge. Beta radiation also changes direction because it has a charge, but gamma radiation has no charge, so it will not deflect. Instead, it will go straight through. Speed. Alpha particles are relatively slow. They are still fast, but relatively slower than the other 2. Beta particles are faster than alpha. Gamma radiation goes at the speed of light, which is 3 times 10 to the power of 8 meters per second. Uses. Alpha radiation is used in smoke detectors. Beta radiation is used to measure the thickness of paper and aluminium foil. Gamma radiation is used as medical tracers, sterilizing medical equipment, and sterilizing soft fruits. Nuclear equations. Uranium-92, 238 turns into thorium plus alpha 2, 4. All we need to do is I just look at the balance. you've got 92 on the left hand side. So here we have 2, obviously this must be 90. Now let's look at the mass numbers. 238 is the mass number. Obviously the left hand side and right hand side should be balanced. So 238 take away 4 gives 234. Let's look at the next one. Carbon 614 turns into nitrogen plus beta radiation. Now the mass numbers should add up to 14. So you can see on the left hand side it's 14. So obviously this must be 14. Now this second part can be a little tricky. The total here is 6. So you need to think, what number should I write here such that the total is 6. So something take away 1 gives me 6. So obviously that must be 7. Let's look at an exam style question. Complete the following nuclear equation by filling in the missing particle. Now I do not know what the particle is, but let's figure out what it is by finding the mass number and the atomic number. 226 take away 222 is 4. 88 take away 86 is 2. So we know it is either alpha, beta, or gamma. It cannot be gamma because gamma is 0, 0. Beta is 0 and -1. Obviously this one must be alpha. Activity. By definition, activity is the number of decays per second, and it is measured in a unit called becquerel. For example, think about a beta emitter that gives out 200 beta particles in 40 seconds. So I need to find the number of decays per second. What I need to do is divide 200 by 40. The answer is 5 decays per second. Half-life is the average time it takes for the number of radioactive nuclei to halve. There is a second version which says it's the average time it takes for the activity to halve. Let's look at a simple example. Say you have a sample of radioactive material with 72,000 atoms to start with. Then after one half-life, this is the symbol for half-life, like T, and a half like that. You can just write the word half-life if you want, and that's okay. Let's say this half-life is 5 hours. So if you check in 5 hours, the number of radioactive atoms will be half of 72,000, which is 36,000. Check it in another 5 hours, it will be half of 36,000, which is 18,000. Give it another 5 hours, it will be 9,000. Another 5 hours, 4,500, so on and so forth. Now here you can see how the activity changes with time on a graph. The initial activity is 800. Now remember, the average time it takes for the activity or number of nuclei to halve is half-life. So what is half of 800? It's 400. You go to the right and you come down, and what is the time? It takes 2 hours. So I can see the half-life here is 2 hours. Now it works just the same way if you go from 400 to 200. Now let's say 400 to 200, you go to the right, you come down, and here is the time, 4 hours. But remember, it started from 400, so we need to get it from 400 to 200. That's obviously 2 hours, the difference is 2 hours. This is the half-life of this particular element. Now, different elements have different half-lives. Sometimes it can be less than a second, sometimes it can be a couple of days, maybe hundreds of years, thousands of years, or even millions of years. And you will be given those values in the exam if they ask a question based on this. You can see a slightly tricky question here. If you want to give it a try, please pause the video and do so, and I will explain in a minute. Now in this one, the initial number of atoms is 600,000 and the half-life is 12 hours. Find the number of atoms left after 3 days. Now this is in hours, this is in days. Obviously 3 days is 3 times 24, which is 72 hours. Now we need to see the number of half-lives. So the number of half-lives is 72 divided by 12, which is 6. So this 600,000 should half 6 times. So if you do it using a calculator, you get 9,375 as the answer. Irradiation and contamination. Imagine you have a radioactive isotope here, and it gives out beta radiation, and it goes to this first apple. In the second example, we have a beta emitter on the apple, or in the apple, on the apple here. Now let's have a proper differentiation here. Irradiation occurs when an object is exposed to radiation from an external source. In contamination, it is on or in an object. Irradiation does not make the object radioactive. Contaminated objects will remain radioactive. Irradiation can be blocked with an adequate shield. If you put some lead here, obviously you can stop it. Contamination cannot be blocked. Once an object is contaminated, it's difficult to reverse it. Irradiation ceases when the source is removed. You remove the source and it is not being irradiated anymore. However, it can be hard to fully decontaminate an object because even if an atom remains, it is still contaminated. Here are some questions on atomic structure for you to try. Please pause the video and do these questions. Here are the answers. Well done for sticking through the whole video. That's a massive achievement. You've now revised all the major topics for Physics Paper 1 and you're definitely more prepared than you were an hour ago. If you found this helpful, please give the video a like and subscribe so you don't miss more revision support. Thanks so much for watching and best of luck with your exams. You've totally got this. For the following